So I'll be talking about a recent paper by Alex and me, which, simulated quantum circuits with select calculus with reduced stabilizer decompositions. And also at the end there will be a bit of work by Renaud Villemar, who has also contributed some new stuff that hasn't appeared in the paper yet. So I'll get to that eventually. So the problem that we're trying to solve is how to somewhat efficiently simulate quantum circuits. Because of course we can't hope to do it actually efficiently, because that's the entire point of quantum computing, is that you can't efficiently simulate it. But we can still try our best. And so broadly, there's two different approaches to doing quantum circuit simulation. The first approach is based on tensor networks. There's a whole bunch of smart things you can do with that. So the basic way is just you do just direct state simulation, where you have your starting state and you consume your gates and you get a more complicated tensor, and then you sort of progress through the circuit. But you can do lots of things to do it smarter. Like you can do principal component analysis to throw away parts of the state that aren't important. You can find better contraction orders, which can really cut down the simulation time. You can cut certain important edges to split your tensor into multiple tensors that you can evaluate independently, and a whole bunch more stuff you can do. So that's one approach to simulating quantum circuits. And the other approach is based on stabilizer decompositions. And there are two different sort of ways to do that. It's either using stabilizer extent or stabilizer rank. And so this talk is about stabilizer rank. And in fact, our approach can sort of be seen, if you squint at it, as a marriage between the stabilizer rank approach and the tensor network approach, where our ZX diagrams are a type of tensor network, and we can view ZX diagram rewriting as a sort of smart contraction of a tensor network. Okay, so let me explain what the stabilizer rank stuff is. So first, we need to know about the Gottesman-Knil theorem. And this theorem says that if we have a quantum computation where we put in a stabilizer state and then we transform it using Clifford unitaries, and then we do a stabilizer measurement, then we can efficiently classically simulate this. And efficiently meaning in time n to the third, where I think it's n squared, where n is the number of qubits, times k, where k is the number of gates, something like that. Another crucial observation is that the stabilizer states span the entire set of quantum states. That means that any quantum state, like psi here, can be written as a linear combination of stabilizer states. And the minimal number of stabilizer states we need to write a state, we call the stabilizer rank of psi. Okay, so I'm going to write the stabilizer rank as these psi's things. Okay, so how do we use this observation to simulate a quantum circuit? So we start with a Clifford+T circuit. You can do other things than T, but Clifford+T is approximately universal, and it's a very popular gate set for fault-tolerant computation. So I'm just going to stick to Clifford+T for the duration of this talk. So we start with Clifford+T circuits, and then we write each T gate as a magic state injection. And what this accomplishes is that now we have the circuit itself is a Clifford circuit, and all the non-Clifford stuff is just captured by these ancillas of magic states at the beginning. Then we can decompose these magic states into sums of stabilizers, and that means that we now have a sum of stabilizer circuits, a sum of Clifford circuits. Then we can efficiently simulate each of these circuits, and then we add the results together. And the way you add these together depends on the specific thing you want to do, if you want to calculate an amplitude, or if you want to calculate a marginal probability, if you want to do something more fancy. And then you're done, you've simulated the thing. So what is the catch of this? Well, it turns out that if we have k of these magic states, then generally the number of stabilizers you need scales exponentially with k. So that means if you have many T magic states, then you need to evaluate an exponential number of Clifford circuits. Then it's still not efficient. But the nice thing is, it's not just like 2 to the k. It's not just exponential in that way. You can actually do something better. You can have something that's still exponential, but sort of polynomially better than 2 to the k. Okay, so how do you do that? Well, let's just first look at a single magic state. So the T magic state that allows you to inject a T gate is just this state. It's a plus state with an extra phase on the 1 here. And this has stabilizer rank 2 because The 0 state is a stabilizer state, and the 1 state is a stabilizer state. This is a sum of 2 stabilizers, so the stabilizer rank 2. And that means if you have k of these things, you just decompose each of them in turn, and that gives you 2 to the k terms. So we know the minimal stabilizer rank of t to the k is at most 2 to the k. Okay, but you can actually do better. For instance, if we have 2 copies of a t magic state, then we get these 4 terms. So naively, we would have a stabilizer rank of 4, because each of these 4 states is a stabilizer state. But we can group them together cleverly. Namely, we can group together the first term here and the last term. And we see we get this 0, 0 plus I, 1, 1. And we recognize this as a Bell state with a S gate on it. And the second part we can group together, we get the 0, 1 plus 1, 0, and we get this e to the I pi 4, but this is now sort of a global phase here. And this is just a Bell state with a NOT gate on it. So we have these 2 entangled Clifford states. And that means that the stabilizer rank of 2 magic states is also 2. And that means that if we have an even number of these t magic states, then we can decompose them in pairs. And then that gives us this number. So we get 2 to the k over 2. So 2 to the 0.5 k. So this is kind of like a quadratic improvement over what you get here, right? So if you decompose t magic states in pairs, it's quadratically better than doing it just naively. It turns out that there's even better decompositions. If you have 6 t magic states, there's a decomposition of this into 7 terms. So that if you sort of calculate it and do some things, it turns out that if you have a large k, then the number of terms needed is smaller than 2 to the alpha k, where alpha is a certain constant, namely 0.467. So this is a bit better than the 0.5 that you get here. Right? So you can decompose 6 into 7. It's better than 2 into 2, because 2 into 2 would give you 6 into 8, which is worse than 6 into 7. So this is a slightly better exponential constant you get. Okay, so that's sort of the classical approach to using stabilized decompositions to do quantum circuit simulation. Now, our idea is to do this, but instead of using quantum circuits, use ZX diagrams. And the benefit of doing that is that we can optimize intermediate ZX diagrams. And those intermediate diagrams might then cancel additional t-gates, and that means that you have to do less decompositions, and that might give you an exponential speed up over this method. Okay, so what's the new algorithm that we propose? Well, we write a Clifford+T circuit as a ZX diagram. That's the first step. That's easy. Like, this is just a straightforward translation. And the next step is you use your favorite algorithm to simplify the diagram. So whatever algorithm you want, you just apply it to the circuit to get rid of as much complexity as possible. Then we pick some of the spiders in the ZX diagram, which have a T-like phase, so a non-Clifford phase. And we decompose these spiders using these magic state decompositions. As a result, we get a bunch of diagrams that we sum together to get the result. And we can simplify each of these diagrams separately. And then we just repeat. We just take each of these diagrams. We again pick a couple of spiders in them. We decompose those spiders. We optimize them again. And we keep doing this until all the diagrams are simple enough that we can evaluate them directly. I describe it here as sort of a breadth first thing, but you can also do it depth first. So you sort of go on one branch of the diagram first, which sort of allows you to restrict the memory usage. That's sort of an implementation detail. Yeah, and we can just evaluate all the diagrams to get your outcome. And then you have your simulation algorithm. Okay. So a bit later, I'll sort of show you how well this works. But first, let's go through these steps in a bit more detail so you understand what's sort of going on here. Okay, so the first step was writing the Clifford+T circuit as a ZX diagram. And this is straightforward, because we have this one-to-one translation between quantum gates and the ZX diagrams. We have the C0 gate, we have an S gate, we have a Hadamard gate, and the T gate. And those are all the gates we need. And then I've also included here a preparation of a state and a effect, sort of a post-selected measurement. And the reason for that is because using these states and effects, we can also represent amplitudes as ZX diagrams. So for instance, if you want to calculate a single amplitude, so we input the 0 computational basis state, we apply unitary, and then we have a certain measurement outcome we want to know the amplitude of, then this becomes just this ZX diagram, where U is now sort of decomposed into C0 S Hadamard T, and then we have these ket input states and this post-selected measurements here. I have here sort of a global scalar factor. You will see these global scalar factors around in a couple of places because I sort of want to present it in like the exact way you get these numbers, but for the simplification reason, complexity reasons, these scalars are really not important. They're just needed to actually get the right outcomes. Okay, so this is how you calculate a single amplitude. But obviously, sometimes you don't care a single amplitude. Like maybe you care about calculating a probability. Well, if you care about the probability of a single measurement outcome, this is simple to get from the amplitude. You just take the absolute value of the amplitude and you square it. But if you want to do a marginal probability, that's a bit more complicated, right? So if you want to know what's the probability that my first qubit is will be measured in the 0 state, but I don't care about the other outcomes. Now, the way you do a marginal probability is you use a doubling technique. Now, I don't know exactly where this was described first. Maybe this can be traced back to Salinger's CPM construction, but I know it's described in this way in the book by Alex and Bob, the Dodo book. So the way you do it is you copy your circuits into the adjoint, and then the measurements that you do want to know you put in the middle, and the marginals you just connect them together, so it gets identity wire here. And then this gives you the marginal probability of these first x1 to xk qubits. Now, a problem here is that if U contains k T gates, then U dagger also contains k T gates. And now we have a circuit of a ZX diagram with 2k non-Clifford things. And seeing as the method is exponential in this number of T magic states, that's kind of bad because we're increasing this number of magic states. But it turns out that because these wires are connected here, lots of stuff will cancel, and we actually don't really see this exponential blow up that much. Like it actually will turn out to be fine. Okay, so that's representing ZX diagram. That's representing circuits and amplitudes and probabilities as ZX diagram. So that's the first step. Then the second, and then let me do a small discussion on types of simulation. So there's two types of simulation we can talk about. There's a weak simulation of quantum circuits, a strong simulation. So weak simulation is where we want to approximately sample from the output distribution of the quantum circuit. So we want to generate bit string samples that have a distribution that's close to the distribution that the quantum circuit would give you, right? That's sort of the canonical simulation thing. But there's a stronger notion of simulation, which is that we can approximately calculate any marginal probability. Now, why is this stronger? Well, there's a way to get from strong simulation to weak simulation, which is we calculate the first marginal, so just the probability that the first qubit is 0, and then we set our qubit 0 with this probability, and otherwise we set it to 1. Then we calculate the second marginal, where we fix the first qubit now, and we calculate the second probability. And then again, we set this value to 0 with the same probability. And we just repeat this until we get a complete sample. And then you can verify that with a product rule that this sample indeed has the same distribution as the quantum circuit. So this is sort of how you get weak simulation from strong simulation with a little bit of overhead. An important note here is that weak simulation is BQP complete. So that means it's as hard as doing quantum circuits. But strong simulation is much harder. It's sharp P complete, which is sort of the complexity of constructing an arbitrary tensor network. And what I will describe here in this talk is actually doing exact strong simulation. So I say here, approximately calculating marginal probabilities, we're actually doing exact calculation of marginal probabilities. Okay, so we're actually doing a really hard task, is the point I'm getting at. Okay. So now let's get to the second step, which is simplifying ZX diagrams. And I'm just going to be describing the standard algorithm that probably quite a few people know that has been used for the T-count reduction kind of stuff, which is essentially trying to get rid of as many Clifford spiders as possible. So the first step is we fuse all spiders, we change all the X spiders into Z spiders, we kill all double Hadamars. So if you have two Hadamars in a row, we can cancel them. We kill all parallel edges, which is with the Hopf rules. If you have two two Hadamard edges between spiders. We can get rid of these edges, and we kill all self loops. This is all sort of standard ZX stuff that you can do. And the resulting diagram is something we call graph-like. So it looks something like this. We only have Z spiders. There's no X spiders. Spiders are only connected via these blue edges, which are these edges with a Hadamard on them. And yeah, there's no self loops. There's only maximally one edge between any two pair of spiders. So it's sort of a nice, simple representation which allows for easy, automatic simplification of diagrams. Okay, there comes the actual simplification, which is trying to get rid of as many spiders as possible. So this first rule is called local complementation. And what's the important part is here from the left-hand side to the right-hand side is we have one less spider on the right-hand side. We have the spider here on the left-hand side with a pi/2 and minus pi/2 phase. And on the right-hand side, this is gone. Okay, and then we change the connectivity of the spiders, but that's really not important. The important part is there's one less spider. And you can apply this to any spider with a pi/2 minus pi/2 phase as long as it's connected only to other spiders. But we will be dealing solely with scalar diagrams. So diagrams have no inputs or outputs. So spiders are only connected to other spiders, right? So we can always do this. We can get rid of all of the spiders with a pi/2 minus pi/2 phase. And the second step removes more spiders. And this targets spiders which have a 0 or a pi phase. And we can apply it whenever we have a connected pair of spiders that both have a 0 or a pi phase. And again, the result is that we remove the spiders and we toggle the connectivity of these things, and we get some scalar factor here. Okay. Again, it's not obvious that these rewrite rules hold, but you can prove them using the standard graphical rewrite rules of ZX. So if you think about this a bit, we have removed all spiders with a pi/2 and minus pi/2 phase. And then for the spider with a 0 or pi phase, as long as they are connected to at least one spider with a 0 pi phase, we can also remove them. So the only spiders left with a 0 pi phase are those that have no neighbors. And if they have no neighbors, then it's just a scalar and we can sort of ignore it. Or they're only connected to spiders which have a non-Clifford phase. So a phase that's not a multiple of pi/2. Okay, so those will be T-like phases. And it turns out we can also do something smart with those spiders. So spiders that have a 0 pi phase that are connected to a non-Clifford spider. What we do with that is we turn it into a phase gadget. So a phase gadget is just the name that we give to this configuration of ZX diagram. So it's a spider with a phase that is connected with a Hadamard edge to a spider which doesn't have a phase. Okay, this is just a phase gadget. And the way we get phase gadgets is if we have a 0 pi phase spider which is connected to this arbitrary phase spider, then we do a variation on this pivot rule, and the end result is that, well, these spiders aren't exactly deleted, but they're sort of combined into this phase gadget thing. Okay, and we view this pair of spiders as sort of a single entity. Okay, so these two different things have become this single entity here. And the reason this is useful is because there's a couple of rules that allow us to kill these phase gadgets. So one thing says that if we have a phase gadget which has just a single leg out of it, right? So a phase gadget can have multiple legs, but if it has a single leg, then we can just fuse it with the thing it's attached to. So the phases combine. And if you have two phase gadgets that have exactly the same set of neighbors, then we can also combine it and we add the phases. And the reason why these rules are really useful is because these, in the diagrams we get, these phases will be typically non-Clifford phases. And then when they combine, we at least have one less non-Clifford phase. And if these both are multiples of pi/4, then actually it becomes Clifford. So then we get rid of two non-Clifford phases and we get a Clifford phase. And we know how to remove Clifford phases because then we can just do that with these rewrite rules. Okay. So if we do these rewrite rules, then we get more Clifford spiders, and then we can remove those Clifford spiders, and the diagram becomes smaller, and we have even less non-Clifford phases. Okay. So the end result is that we end up with a ZX diagram where every spider carries a non-Clifford phase, because if it didn't carry a non-Clifford phase, we could remove it. Or it is the base of a phase gadget, and this phase gadget carries a non-Clifford phase. So the diagram will look something like this. And the reason this is so messy is because this is an actual example of a circuit, an amplitude of a circuit has been simplified in this way. So we see the structure is we have these sort of standard spiders, and then we have these phase gadgets on top. And we see that phase gadgets are never connected together, And that's because if they were connected together, we could do a pivot rule to make them into regular spiders. And the thing that's less obvious is that we have no phase gadget which only has a single neighbor, because if it had a single neighbor, we could remove it. And also every phase gadget has a unique set of neighbors, because if you had two phase gadgets with the same set of neighbors, we could fuse them together using this rule here. Okay, so that's sort of the structure of the diagrams we get at. Now, a nice observation about this is that if the original circuit had KT gates, then the resulting diagram must have at most 2K spiders, okay? So the size of your diagram is independent of the number of qubits of your circuit or the number of gates of your circuit. It only depends on the number of non-Clifford resources that are present in your circuit, okay? By the way, if there's any questions at some point, feel free to interrupt me. Okay. So far optimizing SELEX diagrams. So now let's get to the actual new part of our approach, which is decomposing magic states in SELEX diagrams. Okay, so essentially what we use is I talked before about this thing which allows you to decompose 6 T magic states into 7 stabilizer states, and this is what this decomposition looks like in SELEX calculus. It's not at all obvious that this is the case, by the way. We found this by looking at the decomposition written in terms of stabilizers and then translating those stabilizers into SELEX things and then sort of simplifying them a bit, and we get this representation. So first thing to check is that indeed on the left-hand side, we have these T magic states, so these pi over 4 phases. And on the right-hand side, we can check these are all Clifford diagrams. So they only contain phases that are multiples of pi over 2. Again, we have like these global scalar factors that are not of dot form. That's fine. These are just scalars. Another interesting observation is that the left-hand side is symmetric, right? We can commute the qubits and we get the same state. And if you look on the right-hand side, this is true for almost all the things. So this thing is symmetric, the second and third are symmetric, the fourth and fifth are symmetric, but the sixth and seventh are actually not symmetric. These are actually permutations of each other, these terms. So what is going on here? Well, it turns out that the symmetric set of states of so if we take C2, so the qubit Hilbert space, and we take n tensor copies of those, and we look at the symmetric space, then it turns out this space has dimension n plus 1. So in this case, we have 6 wires here, so we are working in a 7-dimensional space of symmetric states. And it turns out that symmetric stabilizer states only span a 6-dimensional state space. So there is in fact no way to represent this state using just symmetric stabilizer states. So you need some asymmetry here. Okay, it's not really relevant to our approach, but I did think it was an interesting fact to share. Okay, so what do? Well, we have our diagram, and we just pick some spiders essentially at random, and we unfuse a pi over 4 phase, so that we have these 6 T magic states here now. And now we can just apply this magic state decomposition, because we see the left-hand side exactly matches what we have in the bottom here. By the way, here in the diagram, I only picked sort of standard spiders to decompose, but we could have just as well taken the phase gadgets to go into it here. Okay, that doesn't matter for our approach. Okay, so now we apply the magic state decomposition, and then this single diagram splits up into 7 diagrams. And each of these diagrams now has these 6 T-like phases replaced by a Clifford diagram. And that means we can apply our optimization algorithm again to get rid of this Clifford information and result into smaller diagrams, okay? So yeah, if you put this all together, after the first decomposition, we have 7 diagrams. We repeat the whole procedure, so we do the optimization again, and then we do the decomposition again, and then we get 7 times 7 diagrams. And we just repeat this, and we get exponentially many diagrams in principle. And we just repeat it until there aren't 6 magic states to decompose anymore. And that means our diagrams are small enough that we can actually calculate the value of them directly, either by doing just a tensor contraction thing or applying some small decomposition. In any case, like, we can calculate them quite easily. And then we just sum all the values we get, and that gives us the amplitude probability that we were actually calculating. Okay, so that is our approach. So how well does this work? Well, there's 2 things I want to tell about this. First is an asymptotic result, and then there's actual heuristic benchmark results. So the asymptotic benefit. So the worst case scenario is that we do this whole procedure, but we actually never kill any additional T-like phases, right? So the simplification strategy only removes the Clifford spider. We never kill additional magic states. So we just do essentially a standard decomposition, and it doesn't matter if we were optimizing intermediately. Or in fact, it turns out it actually does matter that we optimize intermediately, because if in this case, then at every step, we only need a constant number of rewrites, because we're replacing 6 spiders. These are replaced by a constant number of spiders, and we need a constant number of rewrites to remove those spiders. And since the size of the diagram is order k, where k is the number of T phases, a rewrite will cost order k squared, because we're toggling connectivity between spiders. So that's at most k squared number of connections we need to replace. And there are 2 to the alpha k diagrams, so alpha is this particular constant. So that means the total cost of this procedure is 2 to the alpha k times k squared. And it turns out the original approach, which is given in this paper by Bravyi et al., gave 2 to the alpha k times k to the third. Okay, so we have this polynomial sort of benefit to this method. And the reason for that is that since we're doing this sort of early optimization, we're preventing double work. We can sort of see this as a partial evaluation of the stabilizers, which is done by simplifying the diagrams before we get all the way to the end. Okay. There's an important caveat here, which is that this analysis only works when we're dealing with a single amplitude, because if we're dealing with a marginal probability, in our approach, we're doubling the diagram. So if we're not killing any T-like phases, then we actually have 2 alpha k. So then we have something that's like exponentially worse than this thing we get here. Okay, but again, like in practice, we don't see this 2 alpha k because we get a lot of optimizations. Okay, so then to the benchmarks. So we applied our approach on 2 families of circuits. We applied it to 50 and 100 qubit random Clifford+T circuits, which are built out of Pauli exponentials. If you don't know what Pauli exponentials are, it doesn't really matter for the talk. You can read it in our paper. It's just a sort of nice canonical way to build a Clifford+T circuit. And then the other class of circuits is a class of circuits we call hidden shift circuits, which were also benchmarked in other papers using this stabilized decomposition method. And the only thing important for us here now is that it's a type of CCZ circuit, which is really has a very particular structure. Okay. And so what we are doing is we are sampling from the output distribution, and we're doing that using strong simulation. So we're using this method I described earlier for going from strong simulation to weak simulation by sort of iterating strong simulation n times, and then you get a sample output. So we implemented this in a software library we call Xaxis, which is a Rust implementation of our physics library, which is a lot faster than physics. And we ran this on a dedicated computation server, which is this particular quite powerful Intel machine. And we had a 5-minute limit for every simulation. And if we ran out of time, we just ignored that simulation and sort of graphed only the results we could actually calculate. So this is the first graph. So this is the percentage of circuits we could successfully simulate. So this is for the Clifford+T circuits. And so this is the percentage that we successfully sampled in under 5 minutes. So what we see is for the 50 qubits, for 30, T count 30, we could simulate all of them. And then for 40, we could simulate most of them. And then 50 dropped off rapidly. And with 60, we couldn't simulate any of them. What is interesting and at first quite counterintuitive is that for 100 qubit circuits, we can simulate like much larger circuits, so many, many more T gates. The reason for that is if you think about a fixed number of T gates, and if they're distributed on 50 qubits or 100 qubits, that means in a 100 qubit case, there's way less T gates per qubit. And that means if you're inputting a certain state and have a certain measurement, that it's much more likely you cancel additional T gates because it's a much more low depth circuit. Okay, so our method just finds way more optimizations in this 100 qubit setting, and that's why we can simulate these circuits much more easily. Okay, so then how much better does our method do? Okay, so there's 2 ways in which we can evaluate this. The first is just if we use the naive approach, so where we don't do any optimization or any optimization, we take the circuit and we just start decomposing it, and we can look at the amount of terms that requires to simulate it. versus our method. And we see here there's like order of magnitudes difference in how many terms we need, right? So for this 60 t-count circuit, we see we have like a 10 to the 13 improvement in term count. But a sort of more realistic or more interesting metric is what happens if we take our circuit and we do an initial t-count optimization pass. So we just do what essentially is just a circuit optimization algorithm to simplify the t-count, reduce the t-count, and then we do the naive decomposition. By the way, I call this a BSS decomposition. This stands for Bravyi, Smolin. Sorry, I forgot the third name. It's the original people that came up with the decomposition.
Smith, Bravyi, Smith, Smolin.
Yeah, Bravyi, Smith, Smolin. Thank you. So here we optimize the circuit, and then we do the sort of naive decomposition, and we compare it against our approach. And what we see is that we still get quite some improvement in the term counts. So for instance, we get this like 10 times less terms, which at first sounds quite impressive that you get 10 times less terms. But remember that if you have 6 T-gate extras, that already requires 7 times as many terms. So if you have like say 10 extra T-gates, that sort of accounts for this factor 10. So we can sort of, with this method, simulate circuits with maybe 10 T-gates more, right? Okay. So this is for the Clifford+T circuits, these sort of unstructured random circuits. And we see that our method definitely helps, but it's not like amazing yet. But this picture changes completely when we think about when we look at hidden shift circuits. Okay, so these are much more structured circuits. And again, so these are CCZ circuits. So when we're thinking about T-count, we're taking the T-count is the CCZ count times 7. There's also decompositions of CCZs with using just 4 T-gates, but we found that the decomposition using 7 actually runs a lot faster because you can find many more optimizations. So we worked with the 7 T-gate decomposition. And we see that we can deal with much, much larger circuits, right? So these are 50 qubit circuits, and at the end we see we have 1400 T-gates, and we can still simulate about 20% of them, right? So these are very large circuits, and we can still simulate them under 5 minutes on this cluster. By the way, there is this bump here where somehow if we increase the T-count for a while, we can actually simulate them better, and we have no idea why. So if you have any clue as to why simulation might become easier if you increase the T-count, but if you increase it even more, it becomes harder, please let us know, because it's a complete mystery for us. And what we see here, also the reduction in term count for both these cases, so just the reduction versus the naive approach and the reduction versus where we do a circuit optimization pass and then a naive approach, it also becomes much better, because we see here on the left-hand side, this is log 10, right? So this is literally hundreds of orders of magnitudes less terms. And even here, we see that we get like orders of magnitudes of improvement in terms of terms we need to simulate. Okay, so this is, for these circuits, our method really works well. And we can simulate much, much larger circuits that you can do otherwise. Okay, so what are the conclusions from this? So first conclusion is that optimizing the T-count before using stabilized decomposition is really important, right? Because if you just think about the circuit optimization step, that already helps a lot in both the random Clifford+T cases and the hidden shift circuit case. And the second is that the efficacy of a method depends heavily on the type of circuit. So it's not super useful for the unstructured circuits, but it's very useful for the structured ones. And we haven't looked yet at other types of circuits, but like, it will be interesting to see what will happen if you look at these other types of things. There's also sort of a meta-level conclusion to this, which is that we can't really view optimization and simulation as separate things. They're two sides of the same coin. Because as you saw in our method, we were doing this decomposition and optimization iteratively, right? So doing the simulation step, which is the decomposition, and the optimization step are just two parts of the same thing. We can view a simulation as just a very thorough optimization, right? We're optimizing the thing all the way down to a number, essentially. Okay, so this is all there is in our paper, but since then we've done some extra stuff. So I want to talk about that, but maybe this is a good time to go about questions about this stuff for now, and then I can just carry on to the new stuff.
Can I ask a question? Is extraction necessary after the optimization?
No, so the nice thing about this is that we have a scalar ZX diagram, and the diagram just becomes smaller and smaller. So extraction is, circuit extraction is not necessary anywhere. And that's really cool, because that means we're not restricted in the types of simplifications we can do. Because if you care about circuit extraction, your simplifications must be structured enough that you can get a circuit out at the end. And here we don't care about that. So one of the things you want to look at is which other optimizations can we use now that we don't care about circuit extraction.
Okay. Can you also go back to the VSS slide? The slide with no, after this. It was later. It was much later. The one with the VSS benchmark slide. Next, this one. What is so I'm kind of confused by the difference in the left-hand y-axis and the right-hand y-axis. Orders of magnitude different.
It's the same metric, but just the left-hand side scales sort of exponentially, which is why we have this sort of log plot, and the right-hand side is way less exponential. So we just wrote a regular reduction factor.
Oh, okay. I didn't
sorry for that confusion.
Okay.
So it looks like.
Oh,
sorry.
Do you know, like, for the right-hand side, for the right-hand T count at 4D T count, there's such a discrepancy with the 50 qubits being spread out vertically?
I think we just got lucky. I don't really. Alex, do you have any explanation?
I didn't really understand the question. Could you ask again?
So for the right-hand side for 4D T count, there's just a lot of discrepancy with such edge cases where you just got lucky with the alert.
Oh, I see. Yeah, 40 is sort of more spread out, and then they cluster some more. Yeah. So what tends to happen here is that your we chop off the simulation at 5 minutes. So at that point we just stop and we say that it failed. And as the circuits get bigger and bigger, then the things with large numbers of terms just won't finish before the cutoff. So you sort of lose some part of the graph there in the kind of upper right corner. I think if you put the timeout to 10 minutes or something instead, you'd see a similar kind of spread continuing.
Yeah, because remember, with 40 T counts, we're only looking at about 85% of all circuits, for instance. So 15% of circuits we are not included in this graph.
I see. I had one more question. I'm not sure if I missed it. Was there a definition of what counts as a successful sample? Because what do you measure at the 5 minute cutoff?
We just measured whether we calculated a sample.
Like whether it terminated or?
Yes. Yeah.
Oh, okay. So okay, it's kind of a halting problem thing, isn't it?
Yeah.
Yeah, it's successful if we got a number out within 5 minutes. That's what counts as a successful run.
Well, a bit string. We got a bit string out.
Or we get a bit string out.
So the terms are calculated one by one, and there's not or are they calculated in parallel? Like, is there a notion of how much % of the terms you managed to calculate in a given time? Maybe
we didn't save. I didn't save that sort of how far you get at that point. I mean, I think it will be relatively constant how many terms you can calculate in a fixed amount of time, because they tend to take a similar amount of time as each other.
Oh, okay. So you're saying that every term tends to take the same amount of time?
Yeah, because the diagrams are all of relatively equal size, and yeah, the simplifications actually don't take that much time. So it's really just the number of terms that determines the cost.
Oh, okay. Because I was thinking if some terms are more expensive to to optimize or simulate, then you could just leave them out of the large sum, like missing a few terms here and there might be all right. But if they're all about the same cost, then it doesn't matter.
Well, yeah, I guess it's so we have thought about throwing out terms which have a small contribution to the overall scalar. But yeah, I mean, I guess there's some subtleties there in figuring out, which terms we can ignore and how much error that's going to introduce. But the program itself is also very parallel, so it uses all of the cores on Duvel when it's running. So if one of the terms is taking a very long time, then the other 31 cores are chugging away on different terms.
Oh, okay, thank you.
I have a question. You presented the difference between weak simulation and strong simulation, and you're saying you're doing strong simulation, but you're benchmarking weak simulation. You've also said that going from strong to weak is doable, but it's not. I mean, there's quite some computation involved there. Can you squeeze some extra performance on some other application with using strong simulation directly? What's the reason for using weak simulation in your benchmarks?
So the other approaches, so the other stabilized decomposition approaches, they all do weak simulation, and the way they use their techniques, they can do weak simulation directly. So they're directly sort of estimating, sort of sampling these things. But we haven't figured out how to do that yet using ZX. So that's one of the things we're looking at next. So we're doing this strong to weak kind of thing just to be comparable. And I guess also as sort of like a strongman argument that, like, even though we're doing this harder problem, namely strong simulation, we're still competitive and even do better than their approaches. So that's kind of the point we're making here. But yeah, trying to directly do weak simulation is something we're interested in, but we haven't figured out how to do that yet using ZX.
Is there an application to strong simulation that wouldn't be possible with weak simulation?
So if you think about tensor network contraction, which is very important for, say, condensed matter physics, this is exactly the same problem. Like, it's also this sharp P-Hars problem. So if we can do strong simulation of quantum circuits quickly, it stands to reason we can also do condensed matter type stuff quickly. And stuff like counting sets, like a set as an SAT, the NP-Har problem. The count number solutions, that's a sharp P-Har problem. So that's, like, I'm not sure if there's a use cases for that, but that's at least like something that also resembles this problem.
I think use case is inference or something like that.
Yeah, maybe. Yeah.
Thanks.
Zooming in on people's faces is killing me. It's too good. I also have a question, if you don't mind.
Sure.
So the kinds of circuits which you were testing it on. First there was these Pauli gadget circuits, which I'm guessing were like just randomly generated gadget circuits, and then the other ones were these hidden shift circuits. So it looked like a lot of the success of the procedure came from optimizing away T gates in the initial circuit. Like that was my takeaway from the comparison you showed of the this is the one. Is that the correct interpretation of this? Is that but if these circuits which you're starting off with are these random Pauli gadget circuits, and the simplification thing that you're doing to remove T gates is the ZX-based thing, then we know that the ZX-based thing is equivalent to doing shuffling terms in Pauli gadgets, right? That's the result of Will's paper.
Yeah.
So is there a, I mean, obviously,
so I think the thing you're getting to is we're not just doing circuit optimization, because we also have a specified input state and output state. And if we're calculating a marginal, then many of the qubits are connected together. So way more things cancel than just a naive circle simplification.
Right. Okay. Okay. And that's even at this stage. This is before
Yeah.
you
So
even.
when we say simplified BSS,
decompose.
what we mean is we write our amplitude we're calculating as a ZX diagram, and we do a single round of optimization. So we get this sort of core diagram with only T-like phases. And then we calculate how many terms would we need if we do naive decomposition.
Okay, yeah.
So it's a very strong form of simulation of optimization. It's not just circuit optimization. It's really for every particular choice of measurement effect and input state, and really simplifying the state you have. Sort of Yeah.
Okay, cool. Thanks.
Okay, let me just continue with like the new stuff from here, because we're running out of time, I think. Yeah. So new stuff. So just a couple of days before putting our paper in archive, we found this paper, which actually was in archive for a while. We just haven't found it yet. Improved upper bounds and stabilized rank of magic states. And they do a bunch of really cool things. So first of all, they find an improved stabilized decomposition. For instance, a 6 magic state to 6 stabilizer terms. So instead of 6 to 7, they do 6 to 6, which already improves this exponential constant to 0.43 instead of 0.46. And in fact, this is part of a larger family of decompositions, which sort of asymptotically give you lower values of alpha until alpha is somewhere below 0.4, right? And we were like thinking about this and how to do this in ZX. And then Renaud Villemar reached out to us, and he also he basically was working on the same thing, and he already figured out what we have figured out, but also some more stuff. So yeah, let me just show you what this new stuff is. So this is the result from Qasim et al., sort of the core of that paper, which is this cat6 state, which if you represent it in ZX is this thing. So it's an X spider, which on every leg a pi/4 phase. And it turns out that this thing has stabilizer rank 3. Okay, so this is 6 magic states to 3 terms. So if you could use this directly, that'd be great, because then you have like a really efficient decomposition. The problem, of course, is these things are all connected. They're not separate magic states. And in the paper, Qasim et al., they use this trick where they sort of double the number of terms, and that gives them their 6 to 6 decomposition, and they have 7 magic states. What Renaud came up with is something much smarter, which is that you don't get a stabilized decomposition, you get something that's like a pseudo-stabilized decomposition. So we make the observation that 5 of these magic states is kind of like this state, but with like -4 plugged in, right? Because this thing fuses together, becomes a green phase, and it copies through, so it separates. So we see these things are indeed equal. And then we decompose this thing here, which is 3 terms. So we get 3 terms, but now every term has this pi/4 phase. So we get 3 terms that aren't stabilizers, but that do contain way less magic states. So we go from these 5 magic states single term to 3 terms with each 1 magic state. So we're sort of trading 5 for 1. So when every time we do this, we lose 4 magic states, and it costs us 3 terms. So we get effectively a 4 to 3 decomposition, and that gives us this way better constant. So this is the constant that they get asymptotically, but then we get directly using this decomposition. Okay, so that's the first observation. So you can do a way better decomposition. The second observation is you can actually do better. And that comes down to what I've come to call decorated phase gadgets. So it's a phase gadget, but then on every leg there's a pi/4 phase. And in our diagrams, every phase gadget is a decorated phase gadget, right? So all the legs on the phase gadget contain these pi-like phases, right? Because that's the structure of our diagram. And it turns out that these have very small decompositions as well. Because if you think, for instance, about the cat4 decomposition, so this has a 4 to 2 decomposition. Well, this cat4, well, if you have a phase gadget with 3 legs, we can see this as a cat4 that's sort of post-selected on 1 leg, okay? And so this means we get this 4 to 2 decomposition. So whenever we have a phase gadget with 3 legs, we can decompose this into 2 terms. And this means that as long as we have 3-legged gadgets, we actually have this effective alpha of 0.25, so even much better. So this changes sort of the name of the game, because it tells us that not all magic states are created equally. You have some configurations of magic states that can be decomposed much more efficiently. And that means the game is to look for few-legged gadgets, because it turns out that as long as you have phase gadgets that have 5 legs or fewer, you can do a more efficient decomposition than this sort of generic decomposition you can do here. Okay. So Renault ran some early experiments using these sort of improved decompositions. So these are sort of the preliminary results on that. So these are the time for simulation of our method, so the method I was talking about for like the talk. And then this is using the improved decompositions. And so this is the time distribution for simulation for 50-qubit hidden shift circuits, which have all 16 CCZs. So we see here that using our method, some of them would take like 1,000 seconds to simulate, and this is on Renault's laptop, by the way. While with this improved thing, like everything completed in less than a second, right? So simulation times are just way better, like order of magnitudes better. Okay, so it's going to be exciting to see if we do a bit more data here, like how this is going to work. Okay, so the final conclusions. Using ZX, we can greatly speed up stabilizer simulations, especially if they're structured circuits, so it's hidden shift circuits. And it even allowed us, well, us actually, Renault, to find better decompositions for some substructures of diagrams. So some particular configurations in magic states that turn out to be decomposed in a more efficient way. There's lots of future work and things to try. So the obvious thing is to use more diagram optimizations. So an interesting thing is, for instance, the supplementarity rule, which can also be can be put into a form where you can remove additional magic states. The spider nest identities of Neal and Harney. You have the diagram, you apply the spider nest identities to remove more magic states. It's just something you could, in principle, plug and play, I think. Finding heuristics for picking good spiders to decompose. So it turns out it's really important, or it can make a large difference, which spiders you pick to decompose into magic states. But we haven't found good heuristics yet. We've just tried sort of trying a whole bunch and then picking the best one sort of greedily, and that can make a big difference as well. Yeah, again, like how do we do approximate simulation or direct weak simulation? Here you can think about, for instance, approximate simulation, you can think about throwing away terms that are really small because the scalar prefactors are not created equally. So if you go down a path which like has small scalar prefactors, then maybe you can say, it doesn't matter what this diagram evaluates to, it's going to be a really small contribution, so we can just ignore it. And weak simulation is going to require like really new methods in order to get to that point. And yeah, this whole talk I talked about stabilizer rank. And it's an interesting question to see, can we do something with stabilizer extent as well? And like, yeah, we don't know yet whether there's something there. Okay, that's what I wanted to say. So thanks for your attention, thanks for listening, and here are some papers to read if you want to know more about this stuff. And yeah, thank you.
Hey, John.
Thank you.
I was muted. Do you think with these new decompositions from Renault that you'll see that bump disappearing? The bump you don't understand in the runtime?
Oh, we haven't done that exact simulation because Renault just ran it on a fixed T count and just looked at the distribution of runtimes, and that's a different type of benchmark than we ran, so we haven't compared that yet.
The x-axis on that one was T count, right?
Let me go back. So the x-axis here is runtime.
No,
The first one.
the one with the bump. That was T count.
Yeah.
These are random circuits. Oh, no, they're not.
What are they?
No, they are the
CCZ, right?
Yeah, you're right, you're right.
And it's fixed. Oh, it's fixed 50 qubit size.
Yeah,
Right.
50 qubits. Yeah.
Okay. Right. So that was also my other question. I mean, if you change the number of qubits, do you see the bump again, and does it appear on a different T count? Can you track the location of the bump? I mean, maybe it's not. I mean, is it something universal or not? This is the question. Otherwise, there is no question to understand.
Alex, do you have any input here?
Sorry, I zoned out for a sec. What's the question?
This increase in the number of things we can simulate, did you observe this when doing different qubit counts or slight variations on the experiment?
It does seem to, kind of anecdotally at least, it does seem to sort of go back up at some point. Even changing some of the parameters a bit. But yeah, I don't know for sure. I think maybe it is just fluctuations, really.
Yeah, I mean, for example, if you see this thing appearing for different system sizes, and it just keeps sliding, and its peak appears in different T counts. I mean, that's a thing to understand. If it's just a fluctuation on the 50 qubit one, and then you don't see the same pattern appearing, then you shouldn't be worrying about the drawing.
Yeah. I mean, it might just be we got unlucky with the circuit generated with like a 210, 280 T counts, and they would just happen to be harder. It could have been the case.
Heuristic that picks the right spiders makes it go away. Who knows?
Yeah.
Was it over just one circuit, or did you do like different circuit and make the average to plot this out?
Every T count is 100 different random circuits.
Okay.
So this thing from 75 to 50 is a difference of 25 circuits that could be simulated extra. So 25 on 100, that's like quite significant, I think.
Yeah.
I mean, I don't really know how the hidden shift circuits are structured, but my guess would be that there's just something in them that makes them more amenable. But unless maybe it's just variance, but if it's not just variance, then I would assume that it's just that there's some kind of fortunate structure which makes them more amenable to cancellation at a certain.
Is it possible if you're fixing the number of qubits and increasing the T count, you get more like 2 T's applied sequentially? Right? T's are becoming more dense within the fixed circuit size. So these T's are now turning into S's, and of course the thing is now Clifford.
So more refresh.
Yeah. Because at the moment, like, you get to that point and then the T count is still pretty sparse within the circuit, and now all of a sudden you're just packing in more T gates. You've turned it into something more like a Clifford circuit.
So that doesn't really seem to agree with the results here, where increasing the number of qubits made it easier to simulate, because so there were sparser T gates, right? So there were less T gates per qubit. And that would sort of seem to mean that we shouldn't see that here.
Maybe, yeah. Yeah.
Are the circuit depth constant, or does it increase with T count? How does the circuit depth change with T count?
So we didn't really do depth optimization or anything like that. We just made a circuit with gates. So
I guess he means.
Oh, the gate count, yes.
Yeah, he means in the sample. Like, what's the correlation with T count and the depth in the samples that you're working?
It's linear. It goes linear in the CCZ count. So it's linear in the T count.
Okay.
Yeah.
Okay.
Though at some point it sort of saturates the way that these circuits get built. So you do a CCZ, and then you do some hundreds of diagonal Clifford gates, and then you do another CCZ, and then some diagonal Clifford gates, and so on. This is how you build the classical oracle. But all of these gates compete with each other. So at some point you you saturate in that adding more diagonal Cliffords is not really exploring more sort of space of circuits.
Yeah. Still a pretty big space though.
It's still already at 50 qubits. It's pretty big. Pretty big space. It's sort of like the number of cubic polynomials with 3 variables, or with 50 variables rather.
Right. Yeah.
Because if you just think about this, 1400 T-gates means there's 200 CCZs. Each of the CCZs has 3 qubits, so there's like 600 targets, and there's 50 qubits. So every qubit participates in quite a few CCZs.
Right. Yeah.
So can everyone use this as a simulator?
It's open source, is that what you mean?
But this fancy optimization stabilizer, is it part of the newest release?
So it's definitely like on GitHub, but I can't speak for its user friendliness. Alex ran all the things, so he can maybe say a bit more about it.
Okay.
So the paper links some instructions on how to rerun the experiments, and it basically points to some like shell scripts that run these exact same experiments. And from that, it's kind of clear how you would modify it to do different families of circuits or that sort of thing.
Okay.
Yeah, I have 2 questions. Sorry. So first, so how is it, I'm just curious. So at the beginning you mentioned there is 2 basically general methods. One is the tensor network based. One is the stabilizer decomposition, right?
Mm-hmm.
So in general, how about what's the performance between this? I mean, compared to 2 methods.
The performance difference between the tensor network methods and this method?
And the stabilizer decomposition one. In general, which one is better, or they all?
So they have different scaling behaviors, right? The stabilized decomposition methods, they scale with non-Clifford resources, while the tensor network methods scale naively with number of qubits. But they can also scale with something called the tree width of the tensor network, which is a bit more nebulous in like what it actually corresponds to. You can do lots of fancy things with tensor network as well. Like if you have a noisy quantum circuit, you can sort of use this noise to make your computation run faster. So it's hard to give a one-to-one comparison of which is better. But I'd say like 50 qubit circuits, and like in the case of the CCZs with like literally thousands of gates, I think that you cannot do this on like a consumer server kind of thing using tensor network methods. Like it's just too big.
Okay, thank you. And then I said second one. It's not. It's a kind of comment. So actually this morning I have a paper announced in archive, so which shows how to represent any matrix in algebraic ZX. So I'm just wondering, is it possible? So when you decompose, is it possible to do this way? If we decompose a diagram to a sum of stabilizer diagram, right?
Yeah.
And you start with its matrix, and then you turn this matrix into some simple sums of matrices. Then you turn those simple matrices into diagrams. The thing is,
I think that is essentially what some tensor network people do. Like they realize if you have certain simple tensors, you can write it as a sum of things that disconnect, and then you get a bunch of simpler tensor networks. Sounds a bit like that. I mean, like, there's only one way to be sure that it will work, and that's to do it and see that it works better than other things. That's all the heuristic things, right? Like, it's hard to say in the abstract.
Yeah, sure. Yeah, I just want to know, your feeling, something like that. Yeah, it is realistic. Yes. Yeah. Thanks.
I have a slightly more theoretical question. So it seems like there's a lot of work to try to reduce this alpha exponent. Do we know if there are lower bounds on this thing?
The thing is that the question is like, does it need to be of the form 2 to the alpha k, right? Is there like some better bound that isn't exponential? And I think you can prove that if there is a better bound, then you get some kind of collapse of the hierarchy or some like very unlikely theoretic argument. But the question of like, can we lower bound alpha directly? I do know of a result that says that if alpha is on the order of 10 to the minus 8, then you could use stabilized decomposition methods to beat the state-of-the-art set solver. So then if you just plug it into like a sort of a set solver thing, it would be better than that thing. So it's not a lower bound, but it's sort of saying like, if you get it to that low, it's just a plug and play replacement for set solver things, which is like just an unlikely consequence that like you could do it that way efficiently.
Okay. Because I only know of asymptotic results about stabilizer rank.
Yeah, maybe there's some kind of counting argument to be made that like, oh, we need to represent all these states. So maybe something say like most states will have high stabilizer rank. Maybe you can say something like that. Yeah. I don't know of any formal results.
I've got like a more side question. I saw that you mentioned on the last slide that you want to use spider nest identities on these graph-based ZX diagrams, but I hadn't come across like I've seen some spider nest identities in the normal circuit like scenarios, but not in graph-based ZX. Is that already like something that is out there in a particular paper?
So you mean applying spider nest to ZX diagrams instead of circuits?
To graph-based ZX diagram rather than just normal circuit diagram.
So it's essentially a trivial modification because any ZX diagram can be seen as a circuit with ancilla inputs and post selections. So you just write it like that and then you put it in.
Okay, so generalizes easily. Okay.
Yeah.
I mean, the spider nest identities aren't themselves inherently required to be in circuit form. They're just diagrammatic.
Yeah. I see.
Yeah, and there's also a whole bunch of other things you can do, like for instance, if you have a particular configuration of 7 T-gates, then that forms an H-box, and an H-box has stabilizer rank 2, so then those 7 could be decomposed into 2, like you find that decomposition. Like stuff like that, where like a known configuration corresponds to something with low stabilizer rank. So you could look for those things, for instance.
I guess if you could do spider nest identities, then it follows that you could also throw it into the MATE-ME
Reed-Muller
code, Reed-Muller decoder thing.
So the problem there is the Reed-Muller is really slow.
Right.
And ideally, you want to do this on thousands of diagrams, right?
It's probably worth doing this kind of stuff to the initial diagram at least to get the T count as low as possible. But then it becomes a kind of an interesting trade-off thing of how much time you want to spend optimizing individual terms versus generating fewer terms.
One more question. The phase gadgets with like labeled, the ones that are labeled or something, the one with phase legs, do they have to be pi over 4?
No. So if there's a 3 pi over 4, for instance, you just unfuse a pi over 2 phase. And the nature of pi over 4 is that they're always, if it's a non-Clifford T-like phase, it's always within a Clifford phase of a pi over 4. So you can always infuse a Clifford phase, and that doesn't contribute to anything.
So if the phases are random, what do you do?
If they're not pi over 4 multiples.
Yeah.
So, okay, there's 2 scenarios, right? Either all the angles are different and there's no fixed angle, like just all random. And then there is essentially only the trivial stabilized decomposition you can use. So if you go back to this thing, right? So if instead of a T, we have an arbitrary phase here, well, this thing's still a stabilizer rank 2. But if all your phases are random, that's essentially the best thing you can do. Like there's no reason to believe you will have better decompositions. So you can always do that. And you can still use our method to do that, but then it will be more costly. So a thing that this Kasim et al. Paper does, that's also interesting. So this paper is if you have a circuit where all your non-Clifford phases are equal, so you have a fixed theta, like not necessarily pi over 4, then you can still do non-trivial decompositions. And it's a bit more complicated, but you still get decompositions that are better than the trivial one. So for instance, the Google supremacy circuits, they have this kind of fixed angle that's like a not pi over 4 multiple.
Yeah, that's what I'm getting at, yes. So I'm guessing you tried them, right?
Not yet, I think. Alex, have you tried it?
Dun, dun, dun.
Unmute. No, I haven't tried it yet. Sorry. create a big build up and no, I didn't.
Sorry to put you on the spot, Alex.
Yeah.
Yeah, sequel.
Yeah, but I do think this is a really interesting regime to look at. Or an interesting problem to look at. Because one of the places where you do get circuits with lots of identical but very small phase rotations is if you look at the circuits which come out of Earl Campbell's Q-drift algorithm. So this is a Hamiltonian simulation algorithm. So there, rather than, so it's something which is kind of like trotterization, but rather than having your phase gates, the phases on those gates depending on the coefficients of the Hamiltonian, you take a fixed small phase and then you sample coefficients depending on, or you sample terms of the Hamiltonian depending on the sizes of those coefficients. So you get a circuit with lots and lots of the same but very small phase. And I think this could be a cool way to try to do simulation of those things.
So Aaron uses that to do simulation, classical simulation of quantum dynamics, or is it a proposal for quantum simulation?
Quantum simulation. It's a proposal for quantum simulation. So.
Yeah.
Yeah.
But,
so
but
interesting
if
thing
you're
about
gluing
that.
these things together, it becomes something for doing classical simulation of Hamiltonians. Who knows if it's any better than kind of known techniques for doing classical simulation, but it'd be an interesting thing to try.
Yeah.
So another interesting thing about this is Kasim et al. Decomposition of the fixed magic state thing. If the phase is small, then one of the terms in the stabilized decomposition they find is a very small constant in front of it. So that means if you go down that path where they've chosen that decomposition a couple of times, the pre-constant is so small that you can probably just ignore it at some point. So that you also get you an improvement in like stabilized decomposition. Like we haven't really looked into the statistical arguments there for when we can actually claim this, like, oh, now we're allowed to ignore it because the thing will be small enough. We can probably give an upper bound, like if you have a ZX diagram of a certain size, that like the scale it represents must be smaller than a certain value.
Alex, can I ask for a link to the Oracle CCZ implementation you mentioned for the individual circuit?
Was here, right?
What you mean so the instructions for running this thing, they're in that stabrank.md file. If that's what you mean.
Oh, okay.
The classical Oracle, how it is being generated, you can find that in either in the supplemental material of the Bravyi and Gosset paper or the archive version. But the published version has a bug, so the archive version is better.
Could I ask if you could link it to me? I was looking for applications of qubit CCZ instead of CCX in Oracles.
Yeah, I can probably find it. It should be referenced in our paper, our archive paper that John's talking about here.
Okay, it sounds like the conversation is kind of hitting a lull. So I think unless there's any more people want to fire away now, I'll call it a day. So thanks again to John, and thanks to Miriam for hosting. And next week, the intention